Foveated photon mapping. In this paper, we propose a foveated photon mapping method to illuminate the foveal and peripheral regions with different qualities. We use a gaze tracking hardware, 7-invenson A glass integrated into an HTC Vive to capture the user's gaze point in real time. Here are two eye views on VR HMDs. High-quality illumination is rendered in the foveal regions when the gaze is moving. Our method supports the scenes with various materials and dynamic objects. There is a specular flagon, a glossy teapot, some diffuse apples and cups on the diffuse table. When a piece of transparent jelly falls on the table, the green caustics on the table are rendered in real time. We compare the results of our method with the ground truth and PM3M. The ground truth is rendered by using the traditional photon mapping method with 100 million photons. PM3M is rendered by using the same method as the ground truth with the same number of photons as our method, 3 million photons. We compare the mean squared error of our method with PM3M. The errors are visualized in the images of the second row. The mean squared error of the foveal regions produced by our method is smaller than that of PM3M. In Cornell box, the caustics on the sphere changes accordingly as water waves. We also compare the temporal mean squared error of adjacent frames between our method and PM3M. The normalized temporal errors are shown in the images of the second row. Our temporal mean squared error in the foveal region is similar to that of the ground truth, and is smaller than that of PM3M, because our method reuses the valid foveated photons of the previous frame. Several parameters of our method affect the image quality in the foveal and peripheral regions. The quality changes with the proportion of foveated photons, the number of light photons, and the number of foveated photons. The error in the foveal region decreases as the proportion of foveated photons increases from 20% to 40%, and increases as the proportion of foveated photons increases from 40% to 60%, because if the light photons are too sparse, the flux of foveated photons is incorrectly estimated. The error in the foveal region decreases when the number of light photons increases. The error in the foveal region decreases when the number of foveated photons increases. In all tested scenes, our method achieves interactive frame errors for each eye. Compared with the traditional photon mapping method, which has comparable quality images in the foveal regions, our method is substantially faster than photon mapping and achieves a 9 to 12 times speedup. Even for the photon mapping method with the same photon number, our method is 4 times faster due to 71% to 83% photon reuse. We propose a foveated photon mapping method to render high-quality illumination in the foveal regions for VR applications. Our method uses only 3 million photons, but can generate the same global illumination effect in the foveal region as the traditional photon mapping method using 8 to 12 million photons. Our method speeds up by an order of magnitude.